Welcome back. I want to take a minute and demonstrate how to work through an Excel page called error analysis that goes through some of the computations of error and some of the iterations we did in Matlab. Now, the way that Excel computes things is very different than Matlab, and the first thing that you'll notice is that it stores and shows all the computations along the way. Whereas Matlab, you have to really ask it very nicely with commas to show you all the computation as it goes, because it's assuming that you don't care. And that's kind of the blessing and curse of Excel, is that it shows you everything. And even if you don't care, it shows you all the computations. So it seems more helpful at first, and then becomes really not so helpful, and then impractical, and then impossible to use. So we're not going to use Excel for much in this class, but I just want to show you how easy it is to just do a quick iteration with it. So first, we have the section on error propagation. In this first tab, we'll go through the instructions on how to use the other two tabs, the propagation tab for questions 1, 2, 3 and error propagation, then the precision tab for the testing precision questions 1, 2, 3. So first in propagation, scroll over and you have several sections of yellow, and you want to scroll to the left to see this first box. This is the Babylonian square root method that we did in Matlab, but it's done using Excel, where the first entry is the initial value. Instead of starting at 1, we're starting at 10 this time. And then the next value is the iteration. Right? The previous value, A6, we just click up there, plus 2 divided by A6, just the cell of the previous X value. Error is computed by taking the true minus the approximate. In our case, true is the square root of 2, and I've put the 2 up here, so it's referencing the square root of that number. And I put dollar signs in there because I don't want it to shift as we move cells around. That number is a fixed cell. And then relative error, again, is divided by the true value, so it still has that dollar sign in there. And then you can take this row of computations, and because they're all relative to the previous value, when you scroll down, it'll iterate through. And you should see the values of x as we get closer and closer to square root of 2, pretty quickly. They're right there. And soon enough, it looks like the value doesn't change at all. In fact, the error that is being computed by Excel is stated as 0, which doesn't necessarily mean it is actually 0, but it's so small that it's not going to report anything larger based upon its display precision. Now, what we can do is look at the lowest recorded error to see how that relates to the lowest possible error that Excel could give us. So on this one, it looks like the lowest relative error is about 8 digits. So 2 times 10 to the negative 8. And we know from from the video, that Matlab's machine epsilon is about 2 times 10 to the negative 16th for double precision. So this will be around single precision right here. Then I want you to replicate and do that same thing for y. We'll start off with yn being the initial starting value. In this case, it's 0.3. And then you'll look at the error using the true value of the square root of this cell value. Oh, sorry, that one right there too. And make sure that we put dollar signs between or in front of the 3 so that it's not moving down from that third row. Enter that. Whoop, sorry. True minus the approximate, click, there we go. So I typed in the square root, I clicked on the 2 cell, and then subtracted, clicked on the E6, right? Okay, so there we get my first error. And in relative error, a nice way to do it is simply the error divided by the true value, which is the square root of the 2. Again, relative error is true minus approximate divided by true, but error is true by approximate, so we can use error divided by true to get relative error. And then the next set of yn will be equal to that formula. So I'm going to actually copy the formula over here. Sorry, not the cell. I'm going to go over here and just copy this cell, which copies the formula relative to its placement. So I'm not actually copying the formula. I'm copying the formula relative to its place. So when I paste it, it'll be the formula applied not to A6, but to E6. Very slick. And then I can also copy the error calculation. Let's see how that works. Oh, nice. So then again, it's relative to its placement. So if I paste the whole cell over, there we go. Okay, sometimes the column width is just a little bit too small to represent, to demonstrate all the values that are in that cell. And in this case, it put a bunch of number signs to show you that it couldn't fit. It's a little frustrating, but there's that. Oh, man, get me out of there. Okay. I'm pressing enter to kind of undo the copy that was still in a loop here. So now that I have the second row, I can go through, highlight all those pieces, scroll down, boop, and you can see that's again going to square root of 2, but it's getting there much faster. In this case, the smallest error it accumulates is actually 10 to the negative 12. Well, that's suspicious. That's a much more precise measurement than single precision would have. Is it possible that Excel understands double precision and is just not letting us know it? It's possible. The rest of these cells, you're going to be looking at how error can propagate through addition, subtraction, multiplication, and division. We looked at the error for individual calculations, but when you look at the sum of these two approximations, so say the sum of x plus y at the same level, and we look at the error, well, what's the error? Well, the error is the true minus the approximate. And what's the true? Well, it's square root of 2 plus square root of 2. So 2 times the square root of 2 minus the approximate, this thing right here. And what is the error bound? Well, the theorem for the propagation of error, the bound on the propagation of error for summation is simply the sum of the two errors in absolute value. So equals absolute value of first error plus absolute value of second error. And this red or pinkish colored section right here is going to check to see if the error you have fits within the bounds. And the error itself right now is negative 7.47 and the bound is 9.7. Yeah, that fits. And if we continue by dragging and dropping this all the way down, by dragging and dropping this all the way down, we can see that the error bound is satisfied all the way. In fact, there's no condition, there's no assumptions made on proving that the error in a sum of two approximations is bounded less than or equal to the sum of the two absolute errors. That is always true and can be fairly easily proven using the triangle inequality, which we run into in real analysis. I'll post a bonus video of that proof. It's not in the book and it's not something we necessarily cover in this class, but it's kind of cool. So I'll post that later. Now, before I do everything for you here, I just wanted to point out that what we're doing here is both one, learning how Excel can do similar iterations and error calculations as MATLAB. And two, we're checking some of the theorems that are built into some of the theory we'll be using later. This idea that your relative error is bounded by the machine epsilon, looking for how that relative error compares to the machine epsilon of this particular machine. We'll be looking at how the propagation of error relates to the bounds. If they're always true, or with perhaps maybe some point they become false. If there's something that's just really close that actually just bumps out a little bit. Is there some approximateness to these bounds or not? So let you finish that up. So there you go. 1, propagation tab. 2, the other 4 sections, we're looking at those 2. And 3, which one we did do? Well, I mentioned a little bit, is that you should have all true value. Well, theoretically, we should have all true values. You're not going to get all truths. I don't think so. There will be some false statements that show up, and that's part of the assumptions built into the theorems. Theorems say that the propagation of an approximation will be bounded by the given terms, sometimes in the limit, and not always. So like it'll start out unbounded perhaps, but then the errors will slowly become bounded, like in a discrete series or sequence of values. So I'll let you take a look at that and discuss how tight the bounds are. How does the bound on addition compare to the bound on subtraction? How about multiplication and division? Are they pretty similar, or is one closer to the bound than the other? Let's look at the testing the precision of your devices. Now, testing MATLAB is pretty straightforward. You can use the example code that he had in the book, where you have 4/3, and then you subtract 1, and you multiply by 3, and then you subtract 1 again. And that should be 0, but it yields, in MATLAB at least, it yields the machine epsilon, which is kind of clever. But many of the other devices I've tried it on give you 0. They don't give you anything, any small digit. So instead, let's look at using the definition of the machine epsilon being the next largest number after 1. So you take 1 and you add some arbitrarily small number. And because our machines work in binary, we take that arbitrary small number base 2, right? So we have 1 plus 2 raised to the negative e, where you have this exponent piece. And then we want to subtract 1 to see if there's anything left. If the 2 to the negative e was too small, then 1 plus that number will just round out to 1. And then if you subtract 1 from it, you get 0. So we're looking to see if it's holding on to any significant value. So let's look over at the precision tab and see the example here. We're looking at we're trying to compare the precision of a machine to either single, double, or quad precision based upon the number of bits that are used. Now, single precision, or 32 bits, in decimal looks like 8 digits. 64 bits for double looks like about 16 digits, 2 to the negative 16th or so. And then quad precision, or 128, looks like 39 or 40 digits, somewhere around there. So that's what we're looking at. Instead of just plugging in arbitrary f values, let's try powers of 2. So let me pull up calculator here. A little bit smaller. I use a scientific calculator so I have easy access to the caret button to do powers. And I'm going to start with 1 plus 2 to the, now let's jump ahead a little bit. How about negative 32? Let's do 8 first. Okay, that's obviously bigger than 1. It's not running into 1. We subtract 1 and get, yeah. Okay, so that's obvious. Let's do the same thing with 32 for single precision. 1 plus 2 caret parentheses negative 32. Okay, well, it looks like it's displaying more than just 1, so we subtract 1, we should get the remainder. Again, that's still not the smallest it can be. So then we take 1 plus 2 to the negative 64. Typo, syntax error. 1 plus 2 raised to the parentheses, negative 64. Again, it looks different. It's displaying it different than 1, so when I subtract, e to the negative 20 is my error. Let me try going up to quad precision. 1 plus 2 to the negative 128. Enter. Ah, well, that is interesting. I may have gone too far. It doesn't display numbers different than 1. I'm going to subtract 1, though. Whoa! Now that is looking sharp. Okay, so I'm going to tag it right there. It's possible that it we can go a few decimals past this, but I'm going to tag it at 128. That's a power of 2. It matches up. And I'm going to type in my answer of 2.939 times 10 to the negative 39th. So negative 2.939. I don't need the negative in there. It should take the absolute value. Hopefully it takes the value of it. And then you can write e to represent the times 10 to the power. So negative 39th. Yeah, I probably didn't have a negative. I made it the negative, it seems. Don't put a negative. Moral of the story, don't use it. Don't use negative. Error here. And I don't know why I did negative. That was a mistake. Okay. And this should calculate the number of bits that relate to this decimal number, 128, because that's what I use, 128. And the next biggest power of 2 is 128. And the nearest precision, this would be quad precision. And by the way, this is on my computer. My computer happens to be a Core i7 64-bit computer, which is just a little bit more up to date than my previous computer a few years ago, which looked like it was also quad precision, but didn't quite get up to 128. Now, just for fun, the next multiple of 2 would be 256. Let's just see. If I take 1 plus 2 raised to the negative 256, is that going to be different than 1? Doesn't look like it. Subtract 1? No. Okay, so we know it's not the next level of precision. It's only getting quad precision. That's still pretty good. It's still more than double, which is the standard used in Matlab. Okay, I hope that demonstration was helpful to kind of see how you can test the precision of something like a calculator on the computer. You do the same process on your phone or on your handheld calculator. Just test those numbers out and check those powers of 2. So just see where which of your devices are the most precise in the way that they store numbers. Kind of cool. Well, good luck with that.